Is space-time doomed? You've asked me over and over again what I think of this or what it even means, and what's going on with the amplitude. I think the time has come to finally talk about it. The reason I didn't talk about this previously is that I think it's not remotely as interesting as the headlines in certain magazines would want you to believe, and what could possibly be worse than destroying the enthusiasm of a science lover? So with many apologies, but I think the only reason they write about this at all is that nothing else is happening in the foundations of physics. The amplitude is an idea that was introduced about 10 years ago by Nima Hamed. I've met Nima a few times, and I'd put him among the most intelligent people I've ever met. Witten-Penrose level intelligence, somewhere in the range where IQ scores become meaningless. I don't understand what he's doing in any depth, but I think I can at least help you to put his work into context. On the face of it, the amplitude is a way to simplify calculations in particle physics. You see me using this infographic for the standard model at least 58 times. If you haven't, you should now rewatch all my videos. But mathematically, the standard model is what we call a quantum field theory. It's a framework that tells us what happens when two particles or more interact with each other, at least in principle. I say in principle because while we have the maths for it, we can in many cases not actually calculate much with it. It's just too complicated. In the formalism that we currently use, figuring out what happens when two particles or more get close to each other, for example, because the LHC slams them into each other, requires solving a lot of integrals. And when I say a lot, I mean tens of thousands of integrals or more. There's no exact number because the more precise you want your prediction to be, the more integrals you must solve. Particle physicists usually do this with Feynman diagrams. But Feynman diagrams are just a way to keep track of these integrals. Physicists often interpret them to mean that there is one particle going in and then it hits another particle and that creates a virtual particle and so on. But that's just words. Really what Feynman diagrams are is a funky way to write integrals. The amplitude now is a better way to calculate all those Feynman diagrams. Loosely speaking, it says that the integrals are not all independent of each other. You can collect many, sometimes thousands, together and describe them as a polygon in a higher dimensional space. From this polygon, you can calculate amplitudes from which you can calculate probabilities of measurement outcomes. So a polygon to calculate amplitudes, hence the amplitude. The original version of the amplitude couldn't be used for the standard model, but for other quantum theories that don't describe what we observe, like supersymmetric ones and so on. Mathematically interesting, yes. Physically, not so much. But in the past decade, this research program has grown, and a couple of months ago, the group around Akani Hamed put out several new papers. In these papers, they explain how this approach can also be used without supersymmetry and for some composite particles that actually exist, such as pions. And this is all well and good. The issue with all these Feynman diagrams is indeed a long-standing problem that's holding back our understanding of particle physics. And it's plausible that there are better ways to do the calculations. But in the end, it's just a better way to do calculations. That makes it sound rather boring, and that's why some popular news outlets have tried to make you believe that it reveals a deeper truth, namely that space-time itself doesn't exist. The rationale for this claim is that amplitude are not objects in space-time. They live in this abstract higher dimensional space, yet they still encode properties of space-time. For example, that interactions between particles can only happen if the particles meet. This is called locality. So if the amplitude can tell us something about space and time and the particles in it, maybe what's real is this amplitude and not space-time. Hence the idea that space-time is doomed. It's about to be replaced by something else, like the amplitude, or depending on whom you ask, loops or hypergraphs or 8-dimensional carrots, who knows. I think this is all nonsense, and little Albert agrees. For one thing, quantum mechanics, a theory that's more than a century old, is not a theory in space-time either. It's a theory in an infinite-dimensional Hilbert space. So if space-time is doomed, it's been doomed for a long time, and no one cared. More importantly, one shouldn't mistake maths for reality. We say space and time are real because they're useful to describe our observations. We know that they are, amplitude-hedron or not, so they'll remain real. I agree that it's possible that reformulating particle physics with the amplitude-hedron will help making it compatible with Einstein's theories of space and time. This could be because maybe if you make the amplitude-hedron more complicated, then you also get gravity out of it. But so far, no one's managed to do that. So space and time are fine. They just politely ask that you respect their privacy. And my attitude to the amplitude-hedron stuff is at the moment it's potentially useful, but let's wait and see. It might not be the savior of physics, but it might make those thousands of integrals slightly less annoying. And sometimes that's really all we can ask for in life, isn't it? Did you know there's a free and easy way to learn more about the science behind all the videos that you've been watching? Yes, there is. Have a look at brilliant.org. All courses on Brilliant have interactive visualizations and come with follow-up questions. I found it to be very effective to learn something new. It really gives you a feeling for what's going on and helps you build general problem-solving skills. They cover a large variety of topics in science, computer science and maths, from general scientific thinking to dedicated courses on differential equations or large language models. And they're adding new courses each month. It's a fast and easy way to learn, and you can do it whenever and wherever you have the time. I even have my own course on Brilliant. That's an introduction to quantum mechanics. It'll help you understand what a wave function is and what the difference is between superpositions and entanglement. It also covers interference, the uncertainty principle, and Bell's theorem. And after that, you can continue maybe with their course on quantum computing or differential equations. And of course, I have a special offer for users of this channel. If you use my link brilliant.org/Sabine, you'll get to try out everything Brilliant has to offer for a full 30 days. And you'll get 20% off the annual premium subscription. So go and check this out. Thanks for watching. See you tomorrow.